we doing? Hello! Welcome. All right, here we go, round two. So we start with some decent background today. We'll do our linear systems. You'll recognize these slides from last year, although I think you were all sleeping during that lecture because it was the end of the semester. So we'll do them again, and we're going to use linear systems state space throughout here. So I do want to go over them, especially for the few people that weren't in MTE 360. And then we move on to probability. So we'll cover Bayes' law, Gaussian distributions, and both of which we'll rely on heavily. And then there's an optimization set of lecture slides, but we'll skip those and use them later in the course when we get to the planning section. Although we will be doing some optimization, so I may work in some of it as we get to those pieces. So just a couple of things before we get started today. There was a group I was chatting with about a mechatronics design project yesterday, and I've got another idea for you if you're interested, so come see me after. Or if anyone's still looking for a Tron design project, I have one in collaboration with a civil prof who called me today and asked for a pretty cool design on a pair of huskies that are going to eliminate vibration on bridges by being positioned in the right spots and then actively eliminating vibration at those nodes on the bridge. So you have to automate the ground vehicles moving and deploy these little arms to damp the vibration, essentially. The other thing was, I did promise a few professors at a conference last year that when I started up this course again, I would pitch that any of you that really want to do robotics research know that you can go to their labs. So they loved your previous graduates. We had a couple of guys out of this class. One went to Georgia Tech and worked with Frank Dellert, who's world famous in SLAM. And he begged me last summer to mention it to you that you could all apply, and if I said you were good at this stuff, he would probably hire you. So you can go to Georgia Tech. And Tim Barfoot at Waterloo also will accept you and has frequently pilfered all my favorite graduates. And so also an excellent SLAM researcher. So in Canada, we've got a whole network of us doing this stuff. If you want to go to UBC, if you want to go to Memorial, if you want to go to McGill, let me know, and I'll connect you with the appropriate professors and tell them how well you did in my class. All right? So there's a caveat on that one. Excellent. Okay, so so now I've officially fulfilled my duties as spokesperson for other people's labs, and my lab is also available. So let us know. Cool. So let's get rolling. So today we talk about, this is a hard classroom. Like, how do I do this? I guess, yeah, okay, all right, we're going to wiggle like that. Okay, so quick review. Hopefully it'll all work for you and look familiar. Linear algebra. I'm going to use the following notation. So C is a scalar, a lowercase, right, element of R. B, also lowercase, not bolded, is a vector. So vectors and scalars may get slightly confusing, except that we pretty much always mean vectors. And then matrices with capital letters, and this is also usually, so elements of R, N cross N. So you can have the N's are the number of rows, and M's are the number of columns. And then we're going to refer to fat and skinny matrices. So fat matrices are ones with more columns than rows, right? So they're fat. And skinny matrices are skinny ones, long and tall and skinny, right? And they have more rows than columns, essentially. So it's pretty straightforward. The unit vector is denoted E sub I. So the E sort of refers to a unit vector. So, and the I refers to which element in that vector is 1. And then identity matrix, the capital I, just has the entire diagonal full of 1s and everything else is 0, right? All right. That was hopefully an easy slide. Matrix transpose, so A superscript T, or T is the transpose. We simply flip the matrix, so instead of having A21 as the first element in the second row, we have A21 as the first element in the second column, and we repeat that process the whole way through the matrix. Matrix addition is simply element-wise, so we add A11 to B11 and we get A plus B, right, and we proceed throughout. And matrix multiplication is the multiplication that you know and love, where you take one row from the first matrix in a column and you multiply each element of them, each element together and add up the sum of all of those multiplications and then put that in the first location, right? So it's the first row times the first column of the second matrix in the first spot, et cetera, et cetera. Okay, the matrix transpose of added matrices. So A plus B all transposed is just A transpose plus B transpose. This is pretty obvious. The matrix transpose of multiplied matrices, A times B all transposed, is just B transpose times A transpose. And the quadratic form, and this is one that comes up fairly prominently in the course. We love this one because we can get a closed form solution to it if we want to find its minimum or its maximum. It's quadratic, so it's got a nice oval shape, so there's one minimum or one maximum if it's concave. And so what we end up with here is if I've got a linear expression where x is a vector, A is some matrix that's multiplying it, and B is some vector offsets, right? So think of this as a linear expression in x. The quadratic form then takes that AX plus B transpose, multiplies it by AX plus B, so that's a vector times a vector, right? So you can think of this as x being a row vector in this case, and B is a column. And so what we do, well, we just multiply everything out, so a vector times a vector, sorry for you guys, a vector times a vector is just going to give us a scalar, right? And so we end up with an x transpose A transpose AX as the first term, an x transpose A transpose B, then a B transpose AX, and finally a B transpose B. So each one of those individual terms is a scalar, and we can simplify that down a little bit. Because they're scalars, the transpose is itself. And so the two middle terms that are lumped together to give us 2x transpose A transpose B. And then finally I can sort of rewrite that, just renaming things. So A transpose A, I'm calling C. A transpose B times 2, I'm calling D. And finally, B transpose B, I'm just calling the scalar E. And the reason I write it like this is this first term here, the x transpose CX. That's what a quadratic looks like in matrix form, right? So instead of thinking of it as an x squared, which you get in scalar form, the x transpose with a square matrix C, and then an x after it, that's what I mean when I talk about quadratic form in the matrix. And that's going to show up everywhere. So we'll play with that a little bit more in least squares. We'll play with that when we talk about the optimization to come up with the best estimates, so the EKF, the column filter, all together. Okay, so this is our quadratic term. Awesome. More review, matrix rank. We'll denote that with a row, so the rank of A, row of A. The number of independent rows or columns within the matrix A. And so if we have the same number of independent rows or columns as we have rows or columns which are smaller, then we call the matrix full rank or non-singular. And so row sub A is equal to the minimum of either n or m, where those define the dimensions of your matrix. Similarly, we call it a singular matrix if it's not full rank, so if the number of independent columns are less than n or m, the minimum. And that means as soon as you have a singular matrix, you have some dependence between the rows or columns of the matrix. There therefore exists, so that backwards E is there exists, an x, so a vector x such that when I multiply A times x, I can get 0, right? So that's the null space definition. Does everyone remember all that? Anyone not remember null spaces? Feel free to admit it. It's okay. Okay, almost nobody remembers null spaces. It wasn't supposed to go that far. But all right, there we are. So we will use these kind of concepts, right? Singular and non-singular do matter to us if we're trying to do an estimation process and we don't have full rank on some of the matrices we've got, then we're going to end up with a degenerate solution, which means we're going to have some of the variables we're trying to estimate have no new information about them, and therefore we're going to get zeros or arbitrary numbers in them, and they can totally mess up our entire process. So it is important to remember these things, relate them again to eigenvalues and eigenvectors, which we'll do next. So if you want, maybe brush that up or reread the Wikipedia page on eigenvectors, non-singular matrices, et cetera, et cetera. But it'll all come into focus as we move forward. Okay, so the matrix inverse, right? So A times A inverse is equal to A inverse times A is equal to the identity matrix. It's whatever matrix, when you multiply it by A, gives you that identity. And if we have both a non-singular and square A matrix, right, then it guarantees that it's also invertible, that an A inverse exists, and this is awesome. We're going to use that. The matrix trace, so here's another good one. The trace is just the sum of the diagonal elements of the matrix, right? So AII, right? Only the diagonal elements. A symmetric matrix, so A is equal to A transpose. That means all off-diagonal elements in the same spots essentially are the same, right? So A12 is equal to A21 in this case. And so I've written them as A12. And finally, positive definiteness on this page, at least finally, and semi-definiteness. This gets back to our quadratic form. So a matrix A is considered positive definite if for every possible x in Rn, when you pre-multiply by x transpose and post-multiply by x, you always get a value bigger than 0. Okay? So this is a property of square matrices, symmetric matrices, and we're going to use that as well throughout the course because our covariance matrices and for our probability distributions are all going to be positive. Okay, or well, semi-definite. And so the difference between definite and semi-definite is just the strictly greater than 0 or greater than or equal to 0, right? And so for something to be positive definite, you have to be non-singular, right? Because otherwise the null space would exist for which we know that the right-hand side can be 0, et cetera, et cetera. Okay, excellent. Eigenvalues, eigenvectors, excellent. So for matrix A, the vector x is an eigenvector of A with the corresponding eigenvalue lambda if they satisfy the equation A times x is just equal to lambda times x, right? So you can think of an eigenvector or as a principal direction of the A matrix, right? Whenever I take a vector x and I multiply it by this A matrix, I just get a scaled version of that same vector back, right? So somehow that vector is really important or very closely related to this A matrix, right? And so the eigenvalues actually give us a lot of useful information about the structure of A, and we can use that in all kinds of cool linear algebra tricks. So the eigenvalues of a diagonal matrix are just its diagonal elements, right? And that sort of follows directly from the definition above. And the inverse of A exists if and only if, and sometimes I'll abbreviate that with just IFF, if. None of the eigenvalues are 0. So the inverse will only exist when you have all non-zero eigenvalues, right? There's no null space, therefore the system is not singular, so everything just goes in a circle of 2, right? And so a positive definite A has all of its eigenvalues greater than 0, as it turns out. Therefore, since none of them are 0, it can always be inverted, right? All of these beautiful properties connect and mean that we've got a very nice matrix that we can do a lot of cool things. Okay, excellent. I'm going a little quickly. I'm expecting you to sort of vaguely remember this stuff, but not really. And that as you need it through the course, you'll know that you can refer back to these slides and have it all in one place. And then if ever there's a rule that I'm using that I forget to remind you exists, just ask, and I won't criticize you for, oh, it's in these slides, but that's totally fine. We'll reacquire all this knowledge. Okay, so differentiation of linear matrix equations. This is kind of key and not obvious. So the derivative of the expression AX with respect to X is just the matrix A, and the derivative of X transpose A with respect to X is A transpose, right? And you can actually work through these kind of things by differentiating the individual elements of the expression. It's not really that much fun. Differentiation of a quadratic. This is also very useful. So we have X transpose AX differentiated with respect to the vector X, and so we get the expression X transpose A plus X transpose A transpose. Okay? And again, you can work through the details to confirm that this is true. But really, what we're looking at here is the derivative with respect, the derivative of X with respect to X of that expression is going to be a vector, right? Because X is a vector, so we literally want a derivative for each of the elements of the vector X to know how that expression varies given changes to X. Okay. Least squares. How many of you remember least squares? Wow. All right. How many of you have never heard of least squares before? Okay, at least we're there. All right, good. We're on close. We're close. All right, so we'll go through a little example. I'll bring it all back to you. This is fun, linear algebra stuff. I guess linear algebra really was something you did in first year and never touched again. Is that right? Yeah. This stuff is everywhere, right? Like computers eat linear algebra for breakfast. all I do. Sorry? 5 years ago you guys did it. That's awesome. Okay, so if A is a skinny matrix, so I've got more rows than I have columns, right? And I want to solve or find an x such that A times x equals B, right? So A is going to be skinny, so that means to say there's 100 rows in A, but x is only a 3-element vector, right? And so B is therefore also only a 3-element vector, right? So we're going to have B is going to be a 100-element vector. There we go, that's better. So we've got a 100 by 3 times a 3 by 1 gives us a 100 by 1, and B is also a 100 by 1, right? And we're trying to find the 3 elements of x that make this true. Is that possible? Will there exist 3 elements of x that satisfy all 100 of these individual row equations, right? No. The problem is over-constrained, we call it. I mean, there may be, if you get really lucky, if you repeat the exact same expression 100 times, then yes, there will be a solution. There will actually be an infinite number of solutions. If you only have, so if the A matrix has a rank of 3, then, actually no, that doesn't matter. Okay, so what do we end up with? We have this over-constrained problem, and so instead of trying to find an exact solution that satisfies every single one of these expressions, what we can do is we can try to find a solution that minimizes the error, the sum of errors on all of those individual equations, right? So since A is quite skinny, the problem is over-constrained, so no specific solution exists. And instead what we can try to do is minimize over all possible values of the 3's x states, the quadratic error, we'll call it, so the difference between A times x and B, right? Taking the 2 norm there, so we simply square that error, right? So how do we write that? Well, we write that as ax minus b transpose times ax minus b, right? And we were just talking about that. And so sure enough, we can expand that out, and what we'd like to do is minimize over x the x transpose A transpose times AX minus 2B transpose AX plus B transpose B, right? Okay, so we've switched this problem of trying to exactly satisfy all these constraints into a problem of trying to minimize how far we miss the constraints, essentially, or how much error we permit through. Try to find the best x is essentially what we're trying to do, right? And so how do we solve that problem? Well, this is a minimization, so what are we going to do? Boom, differentiate, exactly right. So we differentiate that expression, we get a 2x transpose A minus 2B transpose A. You just saw me take those derivatives a few slides earlier, so that should be crystal clear, right? So there it is. So I've just taken the derivative. So this last term here has no dependence on x, so its derivative is 0. This term here is a linear expression in x, right? So we just extract that 2B transpose A term. And then finally, this is a quadratic expression here, this x transpose AX. And so we get the 2 times x transpose A term that shows up from the quadratic. Okay, so now this is kind of neat. There's just a single x left in this expression, right? So we can solve for what that x is going to be. So I just manipulate things around. So I move the A transpose B over, or the B transpose A over. I take the transpose of the entire expression, and then I'm left with A transpose A times x is equal to A transpose B. And now I've got this A transpose A I need to get rid of, so what do? I pre-multiply on the left side, both sides of that equation, by A transpose A all inversed, right? Can I just do that willy-nilly? No, I have to know for a fact that A transpose A is invertible, right? And it turns out that it is. We'll just brush that one under the table, shall we? But for any A transpose A, you can do this. And so there we go. So we end up with x is equal to A transpose A inverse times A transpose times B. And so we write that as a pseudo-inverse. I tend to use a dagger, this awesome looking thing, A stab B. And so there you go. So you got your x vector. You now have what's kind of amazing here, right, is we've now found the x that best satisfies that set of equations, the AX equals B set, right? And in fact, what we've done is we've in closed form without ever having to do another optimization, we simply form this A dagger B value, and we get the X immediately. We've got a closed form solution to that optimization problem. And this is why least squares is the first thing you apply to any new problem you've got, right? Because beautiful closed form solution, you just compute it right away, right? Super. It shows up everywhere. The number of times I'm like, oh, this must be an exciting new field, and I flip 3 pages into this new paper, least squares, bam, I'm like, falling asleep. But there you go. It's so powerful. It's always your first go-to tool. Yes?
Right. Can you explain the dagger again?
I call it A stab, just that part, or what? Okay, do you just want the derivation again?
I just don't get what the dagger means.
Oh, sorry, the dagger is, so A dagger is simply the notation I'll use to define, given an A matrix, the pseudo-inverse matrix that allows me to compute this X, which is going to be A transpose A, all inverted, times A transpose. Right? Nothing new, just a renaming. Yeah, exactly. So it's just notation there. Yeah, perfect. Yeah, great question.
I meant to understand this incorrectly. I thought you go A inverse transpose times A transpose. What does that typically give you the identity matrix?
Does A transpose A, all inverted, times A transpose give you the identity matrix? The answer is not quite, no, right? If it was A transpose times A afterwards, right, then yes, you would get an identity matrix and you just get B back. So there's a missing A there for it to be an identity. Great, okay. All right, so it's used everywhere. I think I made that point. Awesome. Okay, so let's do a little example of this. How would you turn a typical problem into a least squares problem? Solve it, what do you get? Sorry, was there another question?
The A transpose A all under would you be able to expand that by saying A transpose as like a 1, combine that with the A transpose to one side identity, that's plug out to A to the negative 1.
So it won't, because you're violating the invertibility, right? Invertibility is a property of square matrices. And so as soon as you break A transpose and A apart, they're no longer invertible. You can't distribute the inverse like you can on a scalar, right? Yeah, no, absolutely. Yeah, you got to be a little bit careful with what you are allowed and not allowed to do with matrices. And so here you literally have to do the multiplication. You'll end up with a square matrix, which turns out to be non-singular, and therefore the inverse exists. And then you can take the inverse, multiply it by A transpose. Make your pseudo-inverse A and multiply it by B to get your answer. Yeah. Excellent. Okay, so here's the problem I came up with. Well, I found. So we have this interesting function. It's 1 over 1 plus 25 t squared. Okay, so for t on the x-axis, I've plotted it in blue. So that's the function right there. And it's this nice little curve. It's somewhat Gaussian looking. It's not a Gaussian, but just sort of a nice curve to try to figure out. So you can imagine this is some response from, I don't know, some sort of physical process that you're measuring, and you have the ability to measure at particular values of t. And then what we're going to do is we're going to get this set of measurements. And so for, in this case, I believe it's something like 50 steps between -1 and 1 for values of t. I've taken a measurement, which I call B of t sub m, where t sub m is the measurement location. And that measurement is plotted on there as a little red circle, right? So these measurements are pretty good, but they're not quite right. They're sort of wobbling around. And the code that I've now uploaded to the Learn actually has the noise parameter right in there, so you can make the noise much larger, you can make the noise much smaller. You can play with this and see how the solution varies. And what we're going to try to do is we're going to try to make our own model of this function using these measurements, right? And why would this be useful? Well, I was just sitting in a meeting this afternoon where one of my students was trying to show me the tire curve, so the way that his tires responded to different acceleration inputs, how much they slipped versus how much they went straight. And I believe you were there too, right? And he had this huge scattering of data, and then it kind of went off like this, and he put a line right on it, boom, right? And he said, that's my model. I'm like, all right, that's pretty good for the linear region. But what about this nonlinear portion over here? Like, what's going on over here? How are you going to capture it, right? So you can imagine, well, let's not use a linear model. Let's use a quadratic model, or let's use something a little bit different and see if we can capture the rest of the effect, right? So we want to take this set of data which has some underlying physical process, and we want to abstract it to a nice simple model that we can then use to predict how that system will act in the future, right? So this is something called system identification. You've probably done it in, say, ME360, and on we go, right? So for this problem, we're going to try to take a polynomial, and this polynomial I'll define an order p, and we're going to try to find the coefficients from x1 all the way up to xp plus 1 that satisfy, that best fit the data that we've collected, okay? So that's the problem I'm going to try to form. So let's go ahead and do that. So I want to do this as a least square minimization problem, right? So I've got 50 different measurements, right? I've got 5 or 6 or 100 different coefficients in my polynomial, right? I can pick however many I'd like. And so I'd like to minimize the error between the polynomial fp, right? That x should not be there, minus the b, which is the measurements that I've received, right? So now I'm starting to form my least squares equation, okay? And so what I need to do is I need to form it in the ax minus b form that we had for our least squares problem. And sorry, this x is really bothering me. That's just so wrong that it's confusing. So I'm just going to remove the x. There we are. Live editing. Awesome. Thank you. Oh. All right. Okay. And so this fp is really just, it can be expressed as an a, which depends on the measurement locations, the t sub n's, and the x, which are the parameters, right, that define, or the coefficients that define my polynomial. And so what do I get? I get basically x1 is the first coefficient. And so for every one of the measurements, x1 is going to be the first element in the x vector. And so the first position in the first column of the A matrix is just going to be 1, because that's just going to add this offset or this bias term x1 to the output, right? Then I've got t1, so x2 times t1, x3 times t1 squared, x4 times et cetera, right? And for every one of my measurements, I have the exact same polynomial, right? But that polynomial is being evaluated at a different value of t. And so for each one of these rows of A, I take the appropriate value of t, and I construct the values of my A matrix, so that when I multiply A times x, I end up with the polynomial f of p at that location, evaluated at that location. Does everyone see that? Pretty much? Awesome. Okay. So there we go. You know what would be really cool would be if I could have the first slide here and then the next slide over here. So you could refer back to, that would be, now we're, all right, somebody got to figure that out for me. Okay, so use least square solution methods to find these coefficients. So we've now got it literally in the form a times x minus b quadratic error. And so we just solve it, right? So we take our pseudo-inverse. We just ask MATLAB. It's got literally a p in command. You can also just use the backslash, and you're off to the races, right? So here's what I've done. Oh, I did only some animations. I'll just flip them all up. So for a fifth order polynomial with only 10 points, you can see in blue the original curve. The red dots are the actual points. And then the magenta line, no, not again. Cyan, thank you, cyan line. You can see the fifth order fit and as best as it can do, essentially, right? And so that's the results you get. And for a 15th order polynomial, of course you can fit it exactly, right? You've got 15 coefficients, but you've got only 10 constraints, so we actually just applied least squares to a least norm problem, right? Anyways, that's another thing for those of you who remember that. So we've overfitted. It means that the polynomial goes exactly through every single point, right? This is a classic problem with overfitting, so you see all kinds of additional oscillations that don't match up with the real data, right? So if instead I just take a lot more samples or a lot more points, then I can, once again, use a fifth order polynomial and fit it through all that data, and you see that doesn't work so well, simply because of the curvature on this function. It's just not well represented by a fifth order polynomial over this entire range. And then finally, for the 15th order polynomial, you can see we do a very good job of approximating the function, especially over the middle region. And then we have a little bit of oscillations down at the end, where the higher order elements of the polynomial are still excited and therefore not fitting the curve exactly. Cool. All right, so that's least squares. Now everyone see how you sort of go through the process? You stack all your measurements, build up the equation that you're trying to minimize, and then use least squares to solve it. Yes? No, these are all new. They should be up now. Yeah. Excellent. They will be up after lecture. Sorry, I must have missed that. Yeah. Thanks a lot. I probably didn't convert it into a PDF and just re-uploaded the old PDF. My apologies. All right. This was a surprise. That's it. Yeah, that's it. I'll go with that. Okay, excellent. All right, so we've got our basic linear algebra organized. We're all set on linear algebra. So now let's try to apply it to the controls domain. And hopefully you remember these slides from the end of the summer semester. So we start from our CISO control, and we'll have some nice PID applications in the lab, driving at constant velocities and turning at constant rotation rates. And so we have our typical plant, so with a transfer function G sub P, right, which has the mapping from inputs U to outputs Y. We feed back that output Y, compare it to some reference signal, and get an error, E. And that error E gets fed into a controller, which has some gain K, and some further transfer function G sub C, which basically takes our errors and maps them to inputs that are going to help us regulate our plant. Right? And so we've designed these controllers and try to stabilize them and ensure that they give us the responses we want. Right? So what's tricky about this is that it basically abstracts all of the inner workings of the plant, all of the higher dimensional things going on, to a single output and a single input mapping. Right? The transfer function kind of loses a lot when we're talking about systems with multiple inputs and multiple outputs. It only represents sort of portions of what's actually going on. And so the idea behind state space control and state space design is to keep track of all that information in a state. So everything you need to know to define exactly how the vehicle, or robot, or system is going to move or progress is captured in that entire state vector. You don't need anything else, right? If you know the state at a particular moment in time, you know how your inputs are going to affect it and how it's going to evolve. Right? And by switching to matrix notation to capture the model, we can then handle multiple inputs and multiple outputs seamlessly with the same algebraic expressions. And this is what makes it really, really cool. All right, so I've just gone ahead and defined this. The state of a system is a vector of system variables that entirely defines the system at a specific instant in time. And so, for example, at t0, knowing all of your initial conditions, that is a state definition, right? And then similarly, and then proceeding on, and we'll go into this a little bit more when we start talking about motion modeling in a week or so. The idea is that if you've got your state information, you no longer need to keep the history of what's happened to your vehicle because everything is captured within that state. All right. Excellent. So we define our standard set of equations for state space systems here in the continuous domain, and this course will mostly work in the discrete domain. But we have our x dot is equal to ax plus bu. So x is our state, and that first equation is our update equation. It defines how our state evolves over time. And the u, of course, is our input, as it was before. And so the a and b matrices define how the state evolves. And then we have a measurement equation, and this one captures whatever information we're able to extract about the state at every instant of time. And so we have a c times x plus a d times u. We expect that our measurements depend entirely on our state and the inputs that we control. Excellent. And for the most part in this course, I'm going to ignore d. It's not actually that prevalent that you have measurements that depend on the inputs you're currently applying. It can be done, but we don't see it very often. Okay, and in the discrete side, we do it very similarly. And this slide is really here to capture the notation we'll use. And so we have an x at time t is equal to a times an x at time t minus 1, so the previous state x, plus a b times u at the current time. And this is sort of a weird notation, but it's the notation that comes directly from Sebastian Thrun's probabilistic robotics book. And so this was, I think, probably a nice set of notation to adopt for the course, because if you're referring to that book first off, but also if you're reading the literature at all, you'll see exactly this notation. This is fairly widely used just because it was in this impressive textbook. Okay, so we have this sort of u at the next time step with the x at the current time step defining the x at the next time step. Right? So just be aware of that. And then for the measurement equation, we have y of t is c times x of t plus d times u of t as we had before. So no changes there. Okay, so we did this little example, and we'll just go through it briefly. We have a spring mass damper here, so the mass has a mass m. It's got a spring with spring coefficient k, a linear spring, and a linear damper with damping coefficient b, which reacts to the velocity. Z is our position, F is an input force, and Z dot will be the velocity, right? And Z double dot will be our acceleration. And so we can form our transfer function by taking the Laplace transform and ignoring initial conditions, and we end up with Z over F transfer function of 1 over ms squared plus bs plus k, right? Okay, so to turn this into a state space model, what we need to do is figure out how big our state is going to be. Well, we have one dynamic equation, which is mz double dot plus bz dot plus kz equals f, right? So we have one constraint on how the motion should evolve. We have control over our input f. So basically 2 degrees of freedom have been eliminated. And we have z double dot, z dot, z and f, basically, which define 4 variables that we're interested in. Everything else are constants. And so that leaves us, so if we have 2 constraints and 4 variables, that leaves us with 2 variables to include in our state. And so we include 2 very obvious ones, z and z dot, right? But you could include any combination of those or representation of those that you'd like, right? You could transform the coordinate systems, you can do whatever you want. But essentially, we know that there's 2 variables that need to be tracked in order to model the system. So we'll pick z and z dot. Awesome. So we can now come up with a motion model. And so we want to do this in the continuous domain. So we take the derivative of our state, so that's z dot and z double dot. And we relate that to the current state by the A matrix. So we end up with a 0 times a 1. So z dot equals z dot is the first expression, plus 0 times f. So the first equation defined by the top rows of the matrix here. And then the second expression is just our standard equation of motion, right? So z double dot is k minus k times z minus b times z dot plus f, and all of that divided by m. So we get exactly our ordinary differential equation that we said. Excellent. Okay, so this defines our A and our B matrices. And we can similarly decide on some measurement system. So in this case, we'll just measure both both Z and Z dot. And so now we have a measurement equation, so we can define a C matrix and a D matrix there as well. And we've now got our state space model, A, B, C, D, boom, we're all set. All right. Excellent. So to relate this concept of the state space model back to our Laplace transforms, our transfer functions, what we can do is we can basically take the standard form, the x dot equals ax plus bu, and the y equals cx plus du, and we can do the Laplace transform on that entire expression. And so we end up with x of s is equal to si minus a inverse times bu. And then when we feed that into the measurement equation, we end up with y of s over u of s is c times s minus a inverse times b plus d, right? So when these are relatively straightforward steps, you can sort of walk through them yourself. But what this means is we have one nice big expression here that gives us a transfer function from y to u. And what's cool about this one is c, a, b, and d are all matrices. So this is a matrix expression, right? And that means that this y of s over u of s is also a matrix, right? And so we're literally going to have a matrix of transfer functions, one from every output to every input. So if we had 4 inputs and 2 outputs, right? In this case, we only have 1 input and 2 outputs. We're going to have a 2-by-1 matrix of transfer functions capturing the relative relationships between all of the inputs and all of the outputs, right? Okay, so if you draw out what that looks like in a block diagram, you get this cool picture. I always like this block diagram. It's just complicated, but doesn't add any clarity. You know, it's just nice. There you go. Sure enough, it works. We've got a little feedback there, a 1 over s integrator. So s times x of s, et cetera, and it all feeds through. You get your outputs y out after you put your inputs u in. And that really is our entire plant model, all in one block diagram. And so if we go through the calculation of this y of s over u of s using the c si minus a inverse b expression, what we can do, and I won't go through the math this time because we've done it before for the most part. Those of you who haven't, hopefully you can walk through it. This is literally a matter of multiplying out matrices. Because it's a 2 by 2, I can do the matrix inversion myself by hand. So there's the matrix inversion with 1 over the determinant. And then I can carry on and do some further calculation, and I end up with these two cool-looking transfer functions, right? So the top one is 1 over m, all over s squared plus b over ms plus k over m, right? And so if I multiply that top expression by m, then I literally get back my original transfer function, right? And this is going to be the transfer function from my input u to my state, right? Or my first measurement, right? And my first measurement was a measurement of z, right? And so sure enough, I get exactly the same expression out for the z over f transfer function that we started from when we derived it ourselves, as we did in controls. And then what's also neat is if we look at the second transfer function, this is from the second measurement, which was the velocity of the mass, right? So z dot. We get the exact same transfer function, but with an s in the numerator, right? And if you remember, an s in the numerator means to differentiate the expression, right? And so sure enough, it's the derivative of z, it's z dot, everything matches up, everything worked out. Okay. The other thing that's kind of cool to look at is if you look at where the transfer functions came from, it came from 1 over the determinant of si minus a, right? And so the roots of the determinant of si minus a turn out to be the poles of our transfer function in our final expression. And so the si minus a only relates to our open loop system, right? And so what this tells us essentially is the stability of our open loop system by looking only at the matrix A. So we can toss everything else out about our system, just take that matrix A, and given that you tell me what the roots of the determinant of si minus A are, you're all set, right? And what's fun about this is the roots of the determinant of si minus A are just the eigenvalues of A, right? So boom, we go type I of whatever our A matrix is, and we immediately have the poles of the transfer functions for our system, and so we can determine our stability directly from our eigenvalues. So, wow, linear algebra is cool. That's what you're supposed to do. It's cool. Wow. Nobody. Just me. It's okay. It's okay. You've seen it already. Okay. So when we add state feedback into this picture, right, we're going to pick a particular u that takes the state x, multiplies it by some main matrix k, right? So we're going to call this full state feedback. So we're replacing u with this value, with this k times our error, right, or k times x, if our reference signal is just zeros. And this is called regulation when we do this. And so we can go back to that same expression, and the only thing that changes is that it now becomes an si minus a plus bk, right? And so now the eigenvalues of a minus bk define the stability of our system, and so we can design our system however we like, right? So since there's 1k for every eigenvalue, right? I just get so excited. There's 1k for every eigenvalue. That means that if we pick k, we can set the eigenvalues wherever we like, right? So instead of all this tedious root locus Bodhi stuff that I made you do 8 months ago, we now can basically just arbitrarily pick k, given full state feedback, right, and place poles wherever we'd like for this state space system, right? So just by defining a slightly different representation and ensuring that you have enough feedback control that you can get to this point, you literally can program your system to behave however you'd like. How am I doing on time? On time. All right, awesome. There we go. So we can place the poles wherever we like, and so this is just an exercise kind of going through the steps. So what do? We add our k matrix in, we multiply it by b, we calculate our determinants, right? And we want to have our poles wherever we like, and then we just do coefficient matching, and sure enough, we get just an expression that k2 over m plus b over m has to equal 10, and k1 over m plus k over m has to equal 50, right? So pick k2 and k1 accordingly, and boom, you placed your poles in the left half plane somewhere in there. Okay. Awesome. Okay. So what is full state feedback in this case? Really? Does anyone remember? What is full state feedback doing? what's the state? Remind me what the state was for this problem. Two values, position and velocity. So I'm doing full state feedback of the position and the derivative of the position, and I'm trying to control the position. What kind of control does that sound like? PD, bang on, right? So in this case, full state feedback is PD. PD control allows us to place the poles anywhere in the left half plane we want, right? In the past, when we were designing PD controllers, we would have picked a D and then varied K, right? Varied our proportional gain, and then looked at what the root locus did or what the Bode plot did and seen a subset of possibilities. But in fact, if we just formulate the problem slightly differently, we can literally just pick a desired outcome and evaluate all options immediately using the power of linear algebra. All right, so there we go. And if we want PID control, we can simply augment our state. We can change our state space representation to also include the integral of Z, right? And so now we just have a 3x3 A matrix and a 3x1 B matrix, and we can now pick 3 gains and set the 3 poles wherever we'd like as well, right? So the same poles. Okay, excellent. So now some things that will relate to what we're going to talk about in the course a bit, but we're not going to see them here. You're going to see them all in your 488 course. I believe you still do that, right? Multivariate? That's next semester, right? Sorry? Oh, it's optional. Okay, you should all do that one.
Did you have to worry in the last slide? Did you have to worry that A isn't full rank?
No, you don't care about A being full rank. You care that A and B are controllable, as it turns out. Yeah. Excellent question. And because you're going to augment with BK, you're going to make it so A minus BK, right? It stays Hurwitz and then everything's good. Yeah. Absolutely. Okay. Excellent. So, can I get there from here? The idea of controllability is essentially given an initial position and a final target position and a finite amount of time, there exists controls that you can apply that will get you from point A to point B, right? So you can arbitrarily vary the state for any A and B locations or any A and B states that you'd like to hit. And so that depends entirely on your definitions of the A and B matrices that you're using. And you can check it very quickly, right? So this rank condition, we just check that the rank of B, AB, A squared B, A to the n minus 1B, that somehow magically works out to be n, right? And there's a pre-programmed MATLAB script that'll do that for you, right? But basically what this is saying is you have enough control authority to make your robot do anything, right? And controllability is a fundamental requirement for solving the optimal control problem, which is one that we'll look at in this class. Awesome. Okay. The next idea is the same thing, but on the estimation or measurement side, and this is called observability, and it says, given that a sequence of states happened between time 0 and time t, right? And given that I took measurements as I went along that path, right? I'm able to exactly determine the state of the system from those measurements. So there's enough information captured in my measurements that I can come up with a good prediction of what the state was, or estimate of what the state was. And that's observability, and it's the analogous concept to the controllability side for control, and we're going to need that in estimation. This is going to be a requirement that my C and A matrix satisfy this condition in order for me to get good estimates and use the filters that we're going to use in this course. And that's it. Yep?
What are you doing with A squared? Is that just A times A?
Absolutely. Yep. Excellent. Okay. So now that we have these concepts of controllability and observability, we can talk about placing, and we have this knowledge that we can place the poles anywhere. The question suddenly changes. How do we come up with a definition for where we should place these poles? And can we get something really awesome? And so the answer is yes. You can actually come up with an optimal control policy, one that minimizes some particular cost metric that you might be interested in. And so here's the cost metric most commonly used. You'll notice it's a quadratic cost, right? We know we're going to have a closed form solution if everything works out right. And it's a cost that works as follows. It's got 2 pieces. The first piece is x transpose q times x, right? And so for the state x, whenever x leaves 0, whenever x is not at the desired 0 location, that's going to incur a penalty, right? So this penalty, if that was the only one, would try to keep the state at 0 all the time, and could use infinite control authority in order to achieve it, right? So it could use whatever inputs you have at maximum, 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 the whole time, just to keep the errors at zero, regardless of what kind of disturbances came in, right? The second half is saying, well, hold on a second, don't just use crazy, insane inputs. Let's penalize your use of inputs as well. And so we have a quadratic cost on the use of your inputs being away from zero, right? And so what we've now formed is this really cool trade-off between allowing the system to have a little bit of error, right, and using only a little bit of control. So in a satellite, you might be very sensitive to using control authority because you had to lift all that gas up into space. So you can have a high penalty on your inputs, but a low penalty on errors in your orbit, right? And maybe in a car, you don't care much. You know, it's a Mustang. You just burn the gas. Nobody cares, right? And you race along at maximum speed, keeping controlling your speed extremely precisely, something like this, right? So different systems will have different trade-offs that work well between how much error you're willing to permit, so how small Q should be, right? And versus how much input you're willing to use and how much power should be. Excellent. So then the other side of this, again, is estimation. And we haven't really talked about this before in the controls class. We sort of assume that you know what's going on. But really, one of the big questions is, given all of the measurement information that I collect about my system, what really is the best estimate of the state that I can come up with, right? And so, again, what we can do is we can slightly change our state space definition now to say that for the evolution of the state, so x dot is equal to ax plus bu, there will always be disturbances that are going to affect how x dot changes. And so I can't exactly know how my state is going to evolve at every point in time. And so I've got this w floating there, which is going to be some sort of disturbance, a wind gust, a bump in the road, anything that's not modeled as part of your A and B expressions, right? And that w is going to corrupt the evolution of x and therefore change the trajectory that x follows, right? And similarly on y, when we take these measurements, they're not going to be perfect. They're going to be close to the value. They're going to be dependent on that value, but there's going to be some electrical noise, or there's going to be some vibration that wasn't expected, or the sensor isn't exactly in the position that you thought it was. And that can all be captured in that V, right? And so the real system has these corrupting influences. The measurements don't tell you exactly what the state is, and the state doesn't evolve exactly the way you expect from the model that you've got for how the state should evolve. And so what we'd like to do is come up with an estimate that best balances the information that we've got. So the predictions from our model with the measurements that we're collecting from our sensors. Okay. Excellent. Okay, so we can make assumptions about all this. We can assume that both V and W are Gaussian distributions, right? So the noise is nicely centered about zero and has a covariance that we can understand, right? So we can model these disturbance effects. And we're going to assume that those covariances, or sorry, that those noise and disturbance sources have covariance Q and R. All right? We're going to assume U is known exactly, and then what we're going to do is we're going to minimize the error in the estimation problem, and it's going to lead us to the Kalman filter, which is one of the core pieces of this course. So we're actually going to do this derivation ourselves and solve this estimation problem as part of the course. And where did it go? I didn't write anything else. What you'll end up with is basically a nice optimization problem again, where we're minimizing, or we're essentially coming up with the best estimate. So the minimum mean squared error between the estimate that we have and the true state that's underlying the system. And that's it. Okay, awesome. And so we put all this together. We've got this plant model that we're developing in the lab from system identification, probably using least squares. We've got an estimator taking every measurement we've got coming out of the system and trying to come up with the best estimate for the state of the system. And then we feed that in to compare it to a reference signal and feed that into a controller. And both the estimator and the controller can be designed in such a way that they satisfy an optimality condition. And so we've got the best of everything, right? We've solved the state space control, estimation and control problem. So hopefully by the end of the course, we'll be at that point. Awesome. All right, how'd I do? Nice, we still have 20 minutes for the next part. Any questions? Everyone tired? No, good, I'm not. We're just getting rolling here, yes. Awesome. Okay, so let's move into probability. This is the other core component of background that we need to understand again. Let me just get rid of that little warning. Oh, sorry. There we are. Okay, so first off, just some notation. Is this going to work? Yes, it's going to work. The probability is the p, lower script p. So the probability of an event A occurring or of A being true is just denoted P of A, right? P of A is always going to fall between 0 and 1. 1 means it happened, and 0 means it doesn't, right? So probability true versus probability false. And the probability of A or B, right, is the probability of A, the probability of A and B is the probability of A or B minus the probability of A and B, right? So we have a typical Venn diagram here where we have our A on the left, our B on the right? The combination A or B, right, is the entire region around, and then the intersection is A and B. And of course, so beautiful Venn, there we go, on that. The discrete random variable, so here we have X, capital X, denoting a random variable, and it's going to take on a countable number of values, so a finite or fixed number of values. And so these are going to be denoted x1 through xn, right? The probability that x takes on a specific value is going to be written as the probability that capital X equals lower x sub I, or just p of x sub I. And an example of this is at the bottom here. So we have a 6-sided die, and if you look really closely, it's not a fair die. Number 3 is actually a little bit higher than 1, 2, 4, 5, 6. So you get lots of 3s out of this die. I couldn't get PowerPoint to get them all aligned. There you go. And I left it because I just think it's awesome. And so the total sum over all the probabilities of each of the individual outcomes being true has to equal 1, right? So you either have to be a 1, a 2, a 3, a 4, a 5, or a 6, right? There we go. X. Continuous random variable we define slightly differently, but they're also very important in the course. So X can take on any value in a continuum, right? The probability density function now describes the probabilities of the X falling in a particular region, right? And so we write the probability that X is an element, X falls between A and B is the integral from A to B of the probability density function P of X, right? Times dx. And so here are some beautiful probability density functions for a continuously varying X. The bluish one looks kind of Gaussian, and the other one looks badly multimodal, right? And so you can imagine trying to figure out what the probability is that the random variable falls in one particular region. Well, where that density function is higher, there's a higher probability that you'll fall in that region, right? So the area under that curve over your interval is going to be the probability that that event is going to fall within that region. Excellent. All right. So measures of distributions, we have a mean, right, which is the expected value of the random variable, the most likely, the central outcome, essentially. Right? And in the discrete case, it's just the sum over all possible outcomes of the value of that outcome times the probability. Right? So xi times p of xi. And in the continuous, it's the integral x times p of x, where p of x is the continuous probability density function. And in every case, I'll refer to the mean as mu, and this will go through everything in the course. We'll use mu over and over and over. Similarly, variance. So here we have the variance is the expected squared deviation from the mean, right? So x minus mu all squared, right? And so the way you calculate that essentially for the discrete case is you take for each value x sub I, you take the difference between it and the mean and multiply that squared times the probability of that particular event occurring. And similarly in the quadratic case, you subtract x from the mean, square it, and multiply it by the probability density function. Okay, so the square root of the variance is the standard deviation. Don't forget that one. And so problems may define the standard deviation, may define the variance, right, back and forth. Don't forget your quadratics. Excellent. More often than not, we'll deal with multivariate distributions, right? So we'll think of the entire state of the robot as a probability distribution, right? We'll think of the measurements as being drawn from probability distributions, et cetera, et cetera. And so we're going to have a multivariable distribution here where capital X is the vector random variable. and it simply denotes x1 through xn as individual random variables. And we're going to have a mean here, so once again denoted mu, where that mean is going to be mu sub 1 to mu sub n, and in each case it's just the expectation of that individual variable. Right? So the mean just is one variable at a time. We're simply stacking their values. And the variance concept is a little more interesting, right? So variance generalizes to covariance in multiple dimensions. And what do we have here? Well, we have our covariance of two random variables that are parts of the vector random variable x, so x sub I and x sub j. The covariance is the expectation of xi minus mu times xj minus mu j, right? And that can be simplified down to the expression below, essentially making it a little bit easier to calculate. Excellent. So what does this covariance mean? Well, if the covariance of x and y for two individual random variables to the part of the vector is greater than 0, right? Then when x happens to be above its mean, then there's a higher likelihood, right, or that y will be above its mean as well, right? So when you have a positive covariance, x and y vary together, right? So a particular sample that comes from x that's higher than its mean means that the y will also be higher than its mean, right? And for negative, it's the opposite. So x varies inversely to y. So when x is inverse above its mean, then it's expected that y will tend to be below. And similarly, if they're independent, then the covariance of x and y is simply 0. There's no correlation between the two. Okay. So you can start interpreting covariance matrices when you see them, right? The diagonal elements simply reconstruct the variance, so the individual variance of the elements in your vector. And then the off-diagonal elements tell you about the relationships between the variables and what one variable will tell you about another variable, essentially. And this will become extremely valuable when you start talking about estimation. Excellent. Okay. So we can capture all of this covariance information in a single covariance matrix sigma. And this sigma is going to be the end goal of our Kalman filter, extended Kalman filter work, right? We're going to calculate not only what the state is, but how well we know it. And this is going to be really useful for planning and for estimation purposes. And the covariance is really just this generalization of the variance, right? So the covariance of xi and xi, so the covariance of xi with itself is just the diagonal element in the covariance matrix, and that is exactly, by definition, the variance of that particular variable, random variable xi. Okay, and then the nice thing to know about covariance matrices is they're symmetric and positive semi-definite, okay? And so we'll use that throughout, and as long as our covariance is positive definite, we know we can have an inverse of it, and we can carry on including inversions wherever we feel. All right. So multiplication by a constant matrix yields a variation to the covariance. So if we look at a covariance for a random variable x, and we pre-multiply that random variable by a constant matrix, right? So whatever outcomes we draw when we're sampling, we just multiply by a, or essentially we're just scaling the outputs of our, the values of our random variable. Well, the covariance changes after a little bit of derivation. You get an a times covariance x times a transpose. And so it's not just a linear variation in the covariance, it's actually got a quadratic. So you're pre and post multiplying by that linear transpose. Excellent. So the covariance of x plus or minus y is the covariance of x plus the covariance of y plus or minus 2 times the covariance of x and y. Yeah, cool. So we can go through the steps essentially, but it's really just a simple expansion. So the first line is just writing out the definition, right? And I use the x plus minus. The plus minus just means either we're doing plus or we're doing minus, right? And then, and so then the expression at the end is also plus minus, showing you that it will be plus when we add them together and minus when we subtract them. And so once you've done the expansion, you simply collect like terms, so the 2 times covariance of x and y, and you get basically your covariance of x plus covariance of y as well. And so if x and y are independent, then the covariance of x plus y is just covariance of x plus the covariance of y, and we'll use this over and over when we're adding new measurements into a set of old measurements and information. Assuming the two are independent, we simply add the new covariance on and carry on. Okay, more probability talk. Here we go. Joint probabilities. So the probability of x and y occurring, right? This is also very valuable. So the probability that x becomes x and that y becomes y is written the probability p of x comma y, right? So this would be something like trying to guess what the probability of clouds and rain are, right? Turns out both happen. Anyways. Independence in this form then looks as follows. So if x and y are independent, then the probability of x and y happening is just the probability of x times the probability of y, right? So the probability of 2 head coin flips in a row is just going to be a quarter. It's a half times a half, both independent events, we'll assume, right? And so you get a very simple calculation for what the joint probability is of 2 heads in a row. Conditional probability, this is also extremely interesting. So the probability of x given information y, right? So the probability of KD for dividend enter given the water engineer is cooking. There's my example. And what we can do is we can relate all this to joint probability. So this is kind of cool. So the probability of x given y is just the probability of x and y divided by the probability that y occurs. All right? And so if x and y are independent, then we have the probability of x given y. Well, y is independent of x, so knowing what your outcome y is has no effect on what your probability of events x are. Therefore, you simply get the probability of x back. Right? And then, in fact, we can calculate by going through the derivation of probability of x and y for independent x and y. Excellent. Okay. So the law of total probability is also valuable. So this says that if x is all of the possibilities that you've got, right, then the probability over all x, the sum of probabilities over all possible outcomes has to sum to 1. And in the continuous case, the integral over all possible outcomes has to sum to 1. So the area under your probability density curve has to sum to 1. With joints and conditional probabilities, we get similar expressions. So the probability of x and y summed over all possible y outcomes is just the probability of x, right? Because y has to be something, and so if you sum over all possible y outcomes, you're just going to get back the probability of x. And similarly, if you have a probability of x given a y times the probability of y, and you sum over all possible y's, you have to end up with the probability of x. All right, good. So we will walk around these over and over and over in our derivations, so I'm showing you them all now, and I'll refer to them frequently as we go forward. It's possible to actually, I think we can do it. Good. It's possible to actually stack discrete variables into vectors to make probability distributions that are just in vector form. So suppose I have a random variable capital X, and it's got n possible outcomes, right? So x1 to xn. Then I can form the probabilities that each one of those events are occurring in a row vector. And I can form conditional probabilities. So the probability if I've got another variable y that's going to tell me information about my x, I can form the probability of x given y is equal to p of x1 given y1, p of x1 given ym, all throughout this matrix. And so we get basically an n by m matrix here of all of the probability, conditional probabilities given the new information in the y variable. And then what's neat about this is I can express my law of total probability using this matrix notation in this case, right? So I've got the probability of x is equal to the sum over all outcomes y of the probability of x given y times the probability of y. And so that just becomes a matrix multiplication of the probability of x given y times the probability of y. So this is pretty good. And then we've got a little note here that shows that all of the columns of p of x given y have to sum to 1. Not that exciting, we'll just carry on. And now we get to kind of the juicy part of the probability section here. This is how we're going to do our estimation process. We're going to take Bayes' rule, and we're going to take new information and incorporate it into an existing hypothesis about what the state is. So wake up, pay attention, here we go, this is important. It turns out that Bayes' rule is really easy to derive. So what do? We've got this expression, the probability of x given y is the probability of x and y happening divided by the probability of just y happening, right? So given that we know that y has occurred, right, we basically just divide out that probability from the x and y happening at the same time, and that gives us our conditional probability. And I can simply rewrite it switching the places for x and y, so I've got probability of y given x there. And now I can start equating things. So I have the probability of x given y times the probability of y is equal to the probability of x and y. And that's also equal to the probability of y given x times the probability of x, right? This was not hard. I just took the denominators and moved them out. And if I just move one more thing, so now I've got the probability of x given y on the left. So I've taken the p of y from that second expression and moved it over to the other side. I get the probability of x given y is equal to the probability of y given x times p of x over p of y. That's Bayes' rule. I'm like, what? That must have taken him like, what, 4 minutes? You know, like what was he doing? He was probably just sipping coffee. I wonder what I should do today. Just fiddling with probabilities. Anyways, it's just so simple, right? It's so beautiful. And it turns out that it has a huge impact. So how are we going to do this? What it's telling us is if we're interested in knowing, given some new valuable information, what I should believe or what I should expect about what's going to happen on X, right? Some variables that I'm interested in. Then all I need to know are these three values here, these three probabilities. And I can update that important information, right? So if I'm interested in what's on the left, right, and I have the likelihood of getting a particular set of new information, given that I'm in a particular state X, and I have the distribution over the entire set of states X, so prior, some idea of how X is represented or what its distribution is, and I divide that through by how often I get that same piece of information, right? So this probability of y of evidence, these three values or these three components basically sum up to tell me everything that I now know about this variable X that I haven't measured, right? And so the way this is going to work for us is as follows, right? If y is actually a measurement, right? So some measurement of a process that we're interested in, a robot position, and x is the current vehicle state, so something we don't know but we'd like to know as well as possible, right? Then what I'm saying here is I'd like to know, given a new measurement, what is the probability that I'm in whatever possible states are available, right? So given that I just measured my GPS location to be exactly here, what's the probability that I'm somewhere in the front of the room, right? That's what I'm trying to figure out, essentially. So, most probable I'm maybe right under this GPS location, but GPS is kind of noisy, so it's probably just as likely I'm over here. It's probably just as likely I'm over here. This is what I'm trying to figure out. Where should I believe I am given GPS information and everything else I've learned about my system in the past, right? And so what we're going to do then is we're going to calculate the probability of y given x. So y given x is, in this case, the probability of getting a particular GPS measurement given that I actually was at that location, right? So the probability of x is going to be the probability that I was at that location somewhere in front of the room, right? So was I there at the previous time step? Did I apply a particular input that would get me to this particular location? So both of those are eminently knowable, right? And then divided by the evidence. How often do I get a particular GPS location measurement? Well, that's kind of a weird one, but as it turns out, we can sweep that one under the rug and get rid of it. And so we can get good models for the first two. And the third one we can normalize out of the way, and therefore we can take this new measurement and come up with the best estimate for what the state's going to be for all of them, right? Okay, and so let's take a totally unrelated example, but a really interesting one, and this will be the last thing we do today. Yeah, we got about 5 minutes to wrap it up. So we're going to apply Bayes' theorem to the following drug testing example. Okay, so a drug test is 99% sensitive, right? So this is a really good drug test. They pay big bucks, top dollar. It will correctly identify a drug user 99% of the time, right? It's also 99% specific, right? So it will correctly identify a non-drug user 99% of the time as well, right? So it's very good at differentiating out non-drug users and drug users. And the company is going to test its employees, 0.5% of whom are drug users. So this is a, upright institution. They don't have a lot of drug users, only 0.5 are users. And the question is, what's the probability that a positive drug test result indicates that an actual drug user has been identified, right? And that's the question. So should they actually trust the output of this test? Well, looks like a good one to me. So let's vote. So all of those in favor of 33%. So the probability that the actual drug user was caught by this drug test, right, is 33%. All in favor, hands up. 1, 2. We got 2 in the front. All right. Oh, the probability, 66%. Who's going 66? 1. All right. 2. 2, 2. Okay. 97%. Who thinks 97%? All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. God, okay. And finally, 99%. Come on, stick them up. Commit to something. The probability that nobody wants to answer? I see about 10. That only adds up to 30. There's at least 60 of you here. You gonna make me do it again? All right, we'll stick with this. We don't have that much time. So we got a bunch of people sitting on the fence. So we had 2, 2, 16, and 10 is our distribution. Awesome. Okay, so let's do the math. Let's apply Bayes' theorem. All right, so here's how we're going to do it. First off, we're going to have 2 groups of users. So we have U are the users and N are the non-users, right? So the set of possible true states, X, are going to be U and N. And we're going to get measurements from these people, right? So we're going to get Y is going to be either a positive or a negative drug test. So either rho or A, right? Excellent. Okay. So we want to find the probability that an employee is a user given that the test is positive, right? So the probability of a user given a positive test. Do you see how I set that up? Right? And so what I need to do is I need to figure out the probability of a positive test given I was a user, times the probability I was a user, all of that divided by the probability of getting a positive test in this result, right? And so this is what Bayes' rule says. We saw that the math is accurate, so it has to be right? And so let's see what we end up with as a result. So the probability that an individual is a drug user was given in the problem. It was 0.5%, so 0.005, P of U 0.005. The likelihood, the probability that a user test is positive given that an individual is a drug user, this was also given in the problem. So the likelihood was probability of a positive test given you're a user, right? And that was 99% accurate. So 99% of the time we catch users, right? And then evidence is the probability, the total probability of a positive test, right? The probability of getting a positive test. There's 2 ways you can get a positive test. You can get a positive test when you're a user, right? And you can get a positive test when you're a non-user. The probability of getting a positive test, given that you're a user, we have is 99%. And the probability of being a user is 0.005%, right? The probability of getting a positive test, given you're a non-user, is 0.01, right? There's a 1% chance you'll get a negative test, a positive test result, even though you're not a user, right? And the probability of being a non-user was 995.995, right? And so that works out to 0.0143. Cool. I still have no insight as to what the answer is. All right. So now we form our Bayes rule, right? And so here we have the probability of being a user, given we got a positive test, is the probability of a positive test given a user times the probability of user divided by the probability of a positive test, right? So probability of a positive test given a user was 99%. The probability of a user was 0.005 divided by the overall probability of getting a positive test was 0.0149 or 143. 143 it should be. And when we multiply that out, we get 0.332. So we get 2 people who got it right, 33% chance that this test actually caught a drug user. So what just happened? How is that possible?
Is it that even just because you're testing so many more non-users that there's a higher chance that a non-user will test positive?
Exactly. And this is the magic of the Bayes rule stuff. This is the magic of probabilistic inference, right? We screw up so many times, right? Oh, that test sounds really accurate. Oh, but I ran it on 995 non-drug users and got 2 positive tests, right? And I ran it on 5 users and got 1 positive test. So of those 3 positive tests, the probability of getting that of any individual in that pool, right, of 3 being an actual user is just 33%, right? And so it was that hidden frequency with which we ran the test on different users, different types, that affected our overall outcome. All right? So there you go. Beautiful. All right, we'll see you. So no lectures next week. I will send out where the tutorial rooms are going to be, and we'll see you the week after. Good luck.